Yes, can you hear me?
Yeah, fine. So the floor is yours.
Okay, thank you very much for introduction. Yeah, and first of all, thank you, Vijay and program committee for this opportunity to speak at this conference. I'm learning very new things, and in next talk it will be a very different topic. So I would like to introduce you some recent development, which I think very exciting for the community of nanoscale fabrication and hopefully also imaging. So we're using femtosecond laser to modify materials on nanoscale, and we want to use this for lithography applications in 2D and in 3D. Okay. Why it is not moving? Okay, so what I will be speaking today is let's have a look at first where there is field, what we can claim that it's already achieved in terms of resolution and throughput. And these are two topics which are always were discussed and from the very beginning. So what resolution, what feature size, what modification we can reach, and certainly if we speak about applications, what kind of throughput we can achieve. And then more interesting and the main part will be where we are going. Can we reach 10 nanometer resolution? Why 10 nanometer is important? If you think about an atom sitting in the silicon lattice, it is making perturbation for electron, which is felt around 5 nanometers. So this is kind of a quantum level requirement to reach 10 nanometer resolution if we can speak to single atom, single defects, for example, for single quantum emitters or single electron devices such as transistors. So for quantum, we really need to reach this level. So can we do this? And then in a few places, I will jump to kind of demonstration that femtosecond laser is actually so nice tool for energy deposition and the precision of energy deposition. Okay, so where we are now. So it's a very long development of 40 years when femtosecond lasers are evolving and people are using them for different applications. And it's a separate story and interesting development. But now we can just take a view where we are now. So the field is matured. What we see in terms of development of laser systems. So for this century, so let's say starting from 2000, what was 1 watt laser, femtosecond laser, now it's approaching 1 kilowatt. In 20 years, we're actually following optical Moore's law. So we are doubling power every 2 years. More or less an amplitude and light conversion laser companies leading in the field, they are confirming this trend. And they say that this can continue. So Moore's law, we know in microelectronics for 60, 70 years. So it looks like we can have very similar development in terms of how we are packing photons in time, similar as we are placing transistors on the chip. So this is very promising for applications. And already almost 10 years ago, laser milling, drilling, removing of materials already reached that rate, which is usually achieved in high precision mechanical manufacturing using CNC machines. So lasers are already kind of 24/7 type of tools in the factory. So this is just we can start from here. But this is for applications which are usually large scale. So this is industry. This is what is bringing investment, and the companies are developing. And I just chose one example, which shows that large areas, so it's tens of centimeters, can be fabricated. This is glass transparent material. You can make holes for optical fibers. All of them should be perfectly aligned. So precision here is around 1 micron, and you can have hundreds of thousands of them on the wafer. And certainly you should not make mistakes when you are making this. So this is how technology is matured if you think about this field. Certainly fabrication on metals, stents, and so on. So this is really very matured field, and this is just second slide, and let's move to something more interesting in terms of science where we can say a few new things. Can we use femtosecond lasers to achieve high resolutions and where we can push it? And the challenge is also 3D, because many things which we are making and technologies we are developing should interface with the 3D world. That's why the scale bar from biology field. So if we are below 100 nanometers, we need really tools how we are modifying and fabricating things at this scale. And very old roadmap picture here is showing that if we look for planar technology, how it is evolved. So once we are reaching 20 or tens of nanometers resolution in terms of resolution node, it's already challenging. Our structures begin to be 3D just for the function to be good transistor. So we somehow, with a planar approach, also having challenges. At the same time, Moore's law is still continuous, and this is also amazing to see how this technology is evolving. If you think how we are making now exposure of chips, it's really very, very demanding. So high resolution is achieved via short wavelengths. So we are shooting CO2 laser, CW laser into droplets, micro droplets of tin in the chamber in vacuum. We should collect light, should handle it. We have reflective optics. We should scan the exposure on the wafer, which is also increasing every time, and it's a very large area. So if you think how demanding this type of fabrication is, it's amazing. Here's some numbers. So if we are changing node from let's say 5 to 4 nanometers lithography, we should invest a huge amount of money. Only 3 countries, and probably Japan is also should be added to this list, can have this technology. If you think in terms of efficiency, you from the wall you should electrical power you should use 1 megawatt to reach 0.5 watt on the wafer when you are exposing your resist. You need many exposures when you are fabricating actual devices. And also something to say that electron beam lithography should be used to define the mask which you are projecting on the wafer. So it's very, very complicated. It's nice achievement of engineering and science, but this is really something which kind of invites us to think, can we do something with simpler techniques? Here we use something what is in the lab and cost 3 orders of magnitude less. So can we reach tens of nanometers modification, machining, lithography tasks? Can we achieve this with the tools using femtosecond lasers? And this is kind of our motivation to do that. Our approach is very simple. So it's actually even simplified pictures simply to convey the message. So it's direct write. So here we are focusing light on the samples. So it could be on the surface, it could be for transparent samples inside or on the backside. So there is flexibility, how you scan beam, how you deliver light on the sample. So it's really direct write. So this is a slower way of modifying materials. However, considering this average power, which is telling also that we have the laser irradiation coming at very high frequency, we can scan and write, we can split the beams, we can do it in parallel. So this technique can be scaled up to more fast throughput. But just to demonstrate principles, we are using something very simple. And if you want, so this is simply microscope development. After 400 years, we are using it now for fabrication rather than just observing micro objects. And focusing here is nothing fancy. We are focusing to this focal spot size, which are comparable with the wavelengths of light. So it's, let's say, 1 micron in diameter. But modification which we can create can be localized much better because we are not bound to the diffraction limit. If we are modifying material at the very tip of intensity distribution, we can do better than wavelengths. That's why we are not limited by and not required to decrease wavelengths in order to have higher resolution. In terms of material science, this is the perfect tool. Femtosecond laser desktop unit can reach with different focusing in different pulse energies this window of fluences. and the affluence divided by pulse duration will be those intensities which you work with terawatt per square centimeter and above. So you can go from excitation and heating up of materials, so it's acoustics. Nonlinear optics is actually even lower. So you start to modify material, you can melt, you can evaporate, you can ionize, and create breakdown plasmas. Before tunneling ionization is somewhere here in this corner. So you see this range, and we can simply choose how much energy we should deliver to our samples in terms of going through the different material modification, different phase transition. And for example, for 3D printing, so this first applications usually in mind are ablation. So you remove material by high power lasers, but also you can 3D print. You polymerize materials. For example, here it's an example for situ. This is in the right place on the map. So you use around 1 terawatt per square centimeter to 3D print polymers. Structures can be very, very tiny and very nice. And you have 3D freedom of writing. Okay, so what is unique about femtosecond laser application in industry so far, and this is what also we want to understand better, is that you can modify initially transparent material. You are focusing usually quite tightly into wavelengths or two wavelengths focal spot, but this is for linear delivery of energy inside transparent material. So how matter is interacting with your laser, with your light, with your intensity defined totally via refractive index. So its permittivity square of it. So usually material is transparent, so in imaginary part is small. But as we increase intensity, and this is happening at the very peak of our femtosecond pulse, we begin to have nonlinear contributions. What we are shown here for absorption coefficient is only 2-photon absorption, the first contribution. Once absorption is increased, we can localize the energy deposition into skin depth, which is proportional 1 divided by absorption coefficient. So this is what happens, that from energy deposition into all focal volume, we can do much better in terms of axial extent of energy deposition. We go to skin depth, and for highly ionized material, it is like in the metal, you can have tens of nanometers thickness where energy is deposited. So the most interesting situation for energy deposition is happening when you have material which is called epsilon near zero. This is when refractive index, real and imaginary part, begin to be very similar. When it is zero, this is definition of dielectric breakdown. So you usually drive material towards dielectric breakdown, but with the controlled energy deposition, because pulses are short, and you can basically know how much energy you deposit with the peak of your oscillating electrical field. You can tune material into different modifications. Also, what is unique for femtosecond pulse is that you deliver energy to electronic system very fast, and all modifications can happen later. And modification, this is what is defined as hydrodynamic movement of material, when ions are moving and atoms rather than electrons. Electrons is they are fast and they are following light cycle. So material begins to be modified, knows that it's modified when energy is coupled to ion systems, and this is usually a few picosecond. Let's remember this number. The most kind of dramatic damage of material you can write inside would be a void, which you formed by micro explosion. And this is example with a few numbers, and it's only one kind of tutorial slide. So void indeed can be created, and when we saw it formed in sapphire, it was kind of interesting. We are focusing below surface, and pulse energy is around 100 nanojoules. And we are focusing to focal spot, which is close to wavelengths. 800 nanometer laser was used here. And what we see after we are opening and milling the energy deposition site, and this is single pulse, we begin to see we see the void, and we can measure its geometry. Because pulses are very short, so there is an invitation to look at this as strong explosion. And strong explosion is how shock waves are generated inside the volume of material. So you need to know three parameters to calculate the two. So it's five parameters are describing your response. So velocity of shock wave, time when shock wave is emerging from the volume where energy is deposited. You need to know energy where it is sitting. And you need to know the geometry, radius of the volume, deposition volume, and density of your host material. So these are simple expressions. So let's have a look at this 100 nanojoules focused into a radius spot with the radius of 330 nanometers. Finally, are producing this type of void. So energy in volume is the same as its pressure by definition. Joules per cubic meter, it's newtons per square meter, so this pressure. So the pressure which is created is huge, and then we know shock velocity, which is around 50 kilometers per second, 5 times more than sound velocity in Sapphire. And also what we can calculate simply from this scaling, that time when shock is emerged from the volume which is modified is actually 4 picosecond. Without any knowledge about coupling of electrons to ions, from strong explosion scenario, we are getting quite right number. And quite dramatically, we can compare this with this event, which is very different. It has 21 order of magnitude larger energy, so this is 25 kiloton nuclear explosion. And it's triggered with the size of 2 meters in the radius, so it's kind of rocket bomb size, which is 7 orders of magnitudes larger than our energy, which is deposited. So this is 21. This is 7 orders of magnitude because cube is sitting here. Hydrodynamically, these two events are defined by the same scaling. So somehow, this is not that we are proving we have the same event here, but just to see on the tutorial level and then simple formulas that energy deposition to the very small nanoscale can be very efficient, and energy deposition, energy density, it's huge. So then we expect that modification around this region where shock wave is modifying region, which is actually not necessarily irradiated with femtosecond laser, can be very high. So we can expect to see high pressure, high temperature materials in this volume, and this is already observed and reported. So, but this is for another day to discuss. The message here is that when we have this energy deposition, which is happening very shallowly because of ionization and breaking material into the absorbing volume inside transparent dielectric, we can deposit energy very efficiently. But now back to lithography. We are interested not in the axial energy deposition, but in the lateral, how small things we can write on the plane. And here we are in the scenario where we are preparing for sample for lithography tasks. So we have transparent substrate, which is glass, and then we are depositing titanium film, 20 nanometers, so to speak, resist. Because we can tune exactly pulse energy that we are ablating at very top of the intensity profile, we can ablate nanohole by a single shot. If we are repeating shots, we see slightly larger ablation structure. And if we repeating, so let's look at those images here on the top, we begin to see this kind of dipole looking dipole scattering would be similar pattern. Yeah, so polarization is light is electrical field oscillating vertically, and we see the scattering of light. But what is interesting that once we have this nanohole ablated, we can reduce pulse energy power by 20%. And then if we are not scanning, we're just irradiating the same spot, what we see that it's evolving as a line, which is not getting wider. And numerical modeling, it's kind of predicting this. This white part is actually blocking intensity here, but it's also marking what kind of structure was modeled here. So there is ablation in the film, and we see how light is distributed. So 80%, 83% of light is really focused on this horizontal line. What is important at the interface, what is defining light intensity distribution, as we see that inside film, we have low intensity, and inside the ablated place where there is air is actually very high. And this comes from requirement for boundary condition that normal component of permittivity should be continuous along the interface when it is dielectric, not conductor. So electrical field in air is much higher than electrical field inside titania. And permittivity is refractive index square. So this difference between refractive indexes titania and air is 2.5. So square of this is 6. And intensity is electrical field square. So intensity is almost 40 times high inside the groove. And this is what you see it's not cartoon, it's really modeling. So focal spot is actually huge. It's 1 micrometer, around 1 micrometer on focus on this side. And how intensity light is distributed in the groove, which is evolving during scanning for this polarization. So normal component is continuous. We have less intensity, and intensity is sitting in the lower refractive index region. So we understand what to expect. Now we also can learn from numerical modeling how to steer our fabrication, because this is only a field ablation, which is controlled by polarization of external laser beams. So if we tune polarization, we can see that we can change orientation where intensity is enhanced. So this would be how you can steer your beam during ablation and writing patterns on the surface of titania nanofilm. So which is shown here. Experimental results shows that up to this curvature of with radius 200 nanometer, you can just steer and ablate the nano groove. What is also interesting that you can write quite closely to two lines, which is absolutely unique for this type of patterning. If you compare with the usual lithography, you always need to recalculate your exposure dose, because the region between two features is overexposed by secondary electrons in the resist. But here, just by the same rule that you have for normal component, electrical field should be lower in your resist, so to speak, in titania here, and it's concentrated in your nano groove. So with the right intensity, which is 80% lower than your nano hole, you can steer it and write, and you can patent areas just by direct writing. And here it's examples. So you're writing nano groove, and you can write them quite closely. Certainly the edges see some structure, so you definitely melt material. At the same time, you can also appreciate, because material is removed and not a lot of it should be removed, so there is not a field of debris. So you really write nano features in your resist with nano-scale precision and definition. And here it's really the question of resolution, because you can write two lines very close. So this is the challenge for resolution. Single feature, single line can always be written because of this threshold effect. But when you write two lines, then you claim resolution, and high resolution can be really obtained. Okay, so this was 2D. So we can do lithography down to tens of nanometer resolution just by direct write of laser, which is focused on 1 micron spot, which is kind of nice and very simple. So can we do something in the volume? You saw that we can ablate in the volume void, so it looks like we can drag this void and write with the structure inside, but this would be a little bit tricky, and the voids we see with this explosions, they are very large. And to find single voids inside volume of your sample is always challenging. So we tend to use Bessel-like beams on space light modulator. This is Bessel beam kind of cartoon. So you have on the axis all the intensity, and those rings are delivering light on the center and along the propagation of your light. So this the pattern was recorded in transparent materials and then investigated. For investigation and final application, it was wet etching was used. So it's for different materials slightly different, but usually it's quite aggressive HF etching hydrofluoric acid. But this is also revealing what is the modification inside. And what we see that we along the propagation of our beam, we see some strange pattern, which is a little bit chaotic. At the same time, if we think look into more details and try to understand how it is evolving. So light propagates from the top, it's very long Bessel beam, and suddenly in some places we see that definitely silica was modified, and that's why it was etched out. Then we can also recognize that we will have some different pattern, which is basically by interference distance separated from the original place. So it's obvious that modified regions are talking to each other, and this is how reflectivity is increasing, and then it's the energy of light scattered from those regions is interacting with the light which comes from the top. So this is propagation from the top downwards for this polarization. So we can actually imagine that just by waiting a little bit in time, pulse by pulse, we can actually evolve with the structures which are quite well localized, and they are getting longer, but not getting much more wider. Let's remember this from the writing on the surface. This was lithography task, but now let's turn it in this orientation to have the same orientation of polarization. So this type of patterning is really happening here, only this is inside the bulk. Here it's example of how we can, by rotating many pulses, how we can make them all into kind of interconnected volumes, which are nanoscale volumes. They are not expanding, and they are just taking place along the focal, along propagation of Bessel beam. Beam is propagating from right to left. And the scanning speed means that we are scanning sample out of plane, out of this image plane. So if it's 9 pulses, it means we are scanning so slowly that until we go 1 micron, 9 pulses will overlap. And if we are scanning even more slowly, like 42 pulses for 1 micron, so we begin to see how the pattern is evolving from kind of random modified regions into regions which are interconnecting with each other. And it's also very obvious that they are not getting wider. The width is defined by kind of natural ability to modify and then to etch out the modified volume. And this is different scale, so it's all 100 microns length, which is modified into single channel, which is very narrow. Because HF is etching silica regardless, it's modified with laser or not, so it's a question of time, how much time you use immersing into etch. And so just to see the smallest features, it was short etching time, we recognize that the line can be very, very narrow. If you etch longer, it's certainly it's widening. But here the aspect ratio is enormous. You have tens of nanometers width for 100 micron length. So what the physics here, what is defining this kind of modification, which is not spreading laterally? And this is slightly different from the previous case when we have really ablated material and low refractive index sitting in nano hole. Here we have situation where on the optical axis at the center of the peak we have ionization of material, so it begins to be more absorbing. So refractive index is decreasing because we have more electrons in this on the optical axis. And then just from Gaussian law, we can derive that localization, this is not wave guiding mode, this is a near field mode, it's not propagating light, but it will be happily sitting in the place where refractive index is slightly smaller for this orientation of polarization. So somehow it's the same like in ablation of titanium film. So if you have slowly decreased refractive index on optical axis, it will be the place where light will be happily localized. and absorbed. And it's also not propagating beam, so it's really light which is localized. Intensity is increased. It's really modifying this nano volume. On the bottom line, there are different materials but measured by different techniques, but what is common is that we are not using etching. We just make very thin films and see, can we recognize modification? And you can recognize that in silica, it's around 10 nanometers, lithium niobate, so you can write domain inversion if you want, and I think people are trying now to do this. In the YAG crystal, you have crystal and amorphous phases very, very well defined, side by side. So then, real example, can we use this to modify material in 3D with nanoscale precision? This was silica exposed with femtosecond bezel beam, slightly below surface. Surface is never damaged, so that's why you can write structures inside, and modification is not changing your energy delivery to those slices inside. Then the sample was polished and etched in the etchant to remove modified regions. And this is what you see. So you recognize that the nano lines are etched out. And there is no any tricks with the critical point dry. It's really just putting sample into etchant and taking it out. Capillary forces here at play, but still you can recognize that high resolution can be obtained.
Dear Professor, I need to interrupt you. We are out
Yeah.
of time, so please summarize.
Yeah, almost finished. So you can do this in different materials. So I showed silica, sapphire, and some other crystals here with the different absorption properties. So 2-photon absorption via multi-photon absorption. So you can write things in the ceramics. You can dye sapphire with this nano knife, changing it by 1 micron. And if you do this, you can create from birefringent material, which is sapphire, you can create lambda quarter plates, which make circular polarized light because you just cut correct thickness of your film. And the same, you can cut any optical element from the slab of glass. For example, for the same function in 2 reflections, you have circular polarized light emerging from Fresnel rhomb, and those surfaces are just laser irradiated and etched out. So this brings me to conclusions. So what I showed that we can use femtosecond laser beam for the task, which would be femtosecond laser lithography down to resolutions of tens of nanometers. Then using similar physics behind that light is localized on nanoscale, and modification can happen down to tens of nanometers, which later you can use for etching structures out. So this is example how you fabricate some volumetric structures of this 3D nanoscale technology with very high aspect ratio. So we know that if we are working at the threshold, the lateral resolution, if it is small, it will be also makes axial resolution smaller, so they are somehow linked. But in the way of this nanofield material modification with the bezel beam, the modification is actually happening because of light scattering and dipolic interaction along the propagation. So aspect ratio down to tens of thousands can be reached. So it's certainly bezel beam fabrication. It's not fair to compare with Gaussian beam, but somehow those numbers are really very, very high. So what I want to say that what was shown that we might have tools using near field. It's very different. It's not propagating field. Near field, we can localize light down to nanoscale and use this as material modification and tool. And this is an invitation to use it for 2D and 3D lithography. So the large team of collaborators over the years. So the theory group from Bordeaux and Australian National University, different times and different people from our group, postdocs and students. Vijay is always we're asking Vijay how to characterize those events from very small volumes and during very short time. So this is ongoing collaboration, and I should say that most of this experimental work, which was really very complex and took a lot of time, this is Zenzili's PhD. So thank you for your attention.
Okay. Thanks again to the speaker, and we have a few minutes or two or one question. So please. Yeah.
Thank you so much for the talk. It's always very interesting to listen to you. I had a very silly question. Why do you need the transparency? What happens if you do this process at high absorption?
Transparency of the sample, right? Yeah, we want to modify inside the volume. So we want transparency inside the volume, but then there is no way how we can deliver energy for required modification. So if you have glass or sapphire and you are focusing your laser, and you are not reaching required intensity, so light just getting through, energy is not delivered, no modification, and you can't benefit from this. So we need to drive material modification in very controlled way. The dielectric breakdown is something less controlled, but just in this epsilon near zero conditions, when we have material where we can deliver energy, as you see, it can be on nanoscale and very well localized, because of that modification is really nanoscale. This is how we can write and modify material. So transparent material needs to become not transparent, but in the places we want.
Okay, thank you. One more.
Hi, Saulius, Shanti here.
Oh, yeah.
Saulius, I was wondering, for the nano knife, what is the aspect ratio that you can achieve?
Yeah, so this is on the slide here. It's 15,000. This was for lithium niobate inscription, so that slicing of silica was close to 9,000. So it's the width is in tens of nanometers, but the length is microns. Yeah, you see here on the top. So bezel beam was defined for the focusing we had. It was 100 micron long, and the modification is around 10 nanometers. But when we etch, it's probably larger. It's larger widths. So still you see the very high aspect ratio.
Okay, thank you. And the last one. Yeah.
Sorry, everyone. Jacob here, Saulius. Great stuff, fantastic stuff. Technology driven, you're talking about kind of a few percent over threshold, ablation threshold for these kind of things to happen. So from a technological point of view, your laser system, how stable are these systems when you start getting to the power levels you're interested in, and
yeah,
the right way?
Yeah, it's a good question. And these days, femtosecond laser machines really very stable. And we're using some results here used with the old titanium sapphire, which was less stable at only 1 kilohertz. But some of results are done with the more new versions of light conversion units, which are well enclosed into this machining setups. They are not really susceptible to changes of their output power. They are very stable. That's why we can really look and reproduce, like single shot is making the same nano hole each time we are shooting some. And I know from the companies that example where many holes for fibers are made inside silica wafer. The tolerances for mistakes is simply not existing. So they need every shot to produce the hole, or expose the volume which later etched out. So the short answer is that lasers are the required stability now.
Okay, thank you once more. Thank you for impressive presentation.